Hey, good morning, guys. Assalamu alaikum. Welcome back to grade 11 Maths by Inspired Teens, where in today's lesson we'll be continuing with Euclidean geometry. Just give me 1 second. I just need to share the YouTube link. Okay, let's give it a minute or two, and then we can start. Let's just wait for a few more people to join, and then we'll start. Okay, I think we can start. Let's go ahead. I'm just trying to remember where we stopped. I think we went up until theorem 4. Okay, just give me 1 second. Okay, I'm going to reshare my screen in a bit. Sorry. Okay, let us start. Sorry for the delays. Let's start finally. Okay, I think we ended here where we discussed angles in the same segment. Okay, let's just recap what we've done so far. So we've done some of the basics, revision of previous work, exterior angle of triangle. We worked through parallel lines, okay, which is important. Okay, we did bisect theorem. Okay, then we discussed some certain concepts I wanted you guys to understand before we continued learning all the theorems. Okay, segments, subtending. What does the word subtend mean? Okay, and so on. Okay, then we discussed theorem 1, which said line from center is perpendicular to chord, right? And then line from center, which is perpendicular to chord, bisects the chord. And if the line from center bisects the chord, it is also perpendicular to that chord. Okay, so that's the things we discussed here. Then we said angle at center is equal to 2 times angle at circumference. Okay, so keeping in mind all these weird examples. So here's the normal one that looks obvious. And there's maybe one like that. That's slightly weird, but still a bit obvious. But then we have this one, which you must keep in mind, where the one of the lines that subtends the circumference angle is the diameter. Okay, but it's still the same concept. Angle at center is equal to 2 times angle at circumference. Okay, and then we discussed what about if the angle at the circumference is in another segment. Okay, and that's how we that's what we did here. Okay, remember we said that the angle, the circumference angle, which is in the other segment, okay, is equal to, it's the circumference angle for which center angle? For the center angle, the reflex center angle at obviously the center. Okay, so the circumference angle in the other segment, okay, is half of the reflex center angle. Okay, so just keep that in mind. Yeah, we solved it was actually 180 minus x. This is double of that, 360 minus 2x. Okay, we did another example there. Then we discussed this theorem, angles in a semicircle. Okay, so angles in a semicircle, they equal to 90 degrees. Okay, so any angle subtended by the diameter is equal to 90. Okay, it's a perpendicular angle. We call it angles in a semicircle because when it's subtended by the diameter, of course, when there's a diameter, it separates the circle into two halves. Okay. Then we discussed angles in the same segment. Okay, so basically these are angles subtended by equal chords. Okay, so in this specific case, right, it's just that the equal chord happens to be the same chord. Okay, so again, like angles subtended by equal chords, they don't even have to be the same chord. Okay, I'm not going to draw. Let's go back to that example. We did this example here, for example, right? Equal chords subtend equal angles. Okay, they're not the same chord, but they're equal in length and they subtend equal angles. Then, of course, a chord that's the same, okay, two different angles which are subtended by the same chord would also be equal, because it naturally follows that previous rule as well. Okay, so yes, and okay, let's move on. Okay, before we do theorem 5, let's discuss some of these things, corollaries, or whatever this word is, doesn't really matter. It's just a few extra things we need to discuss. Equal chords or arcs subtend equal angles at the circumference. We already discussed that. Okay, if that's theta, that's theta. Equal chords subtend equal angles at the center. Now, this is something we haven't discussed, but it's also true. So here we have two circumference angles, okay, being subtended by equal chords. If those same equal chords subtend two center angles, okay, those center angles would also be equal to one another. Okay, so that's something interesting to keep in mind. Okay, if they subtend equal angles at the center, if they subtend angles at the center and they equal chords, those center angles would also be equal. Okay, and then let's have a look at this. Equal chords in equal circles subtend angles at their circumference. Subtend equal angles at their circumference. Equal chords. Okay, so basically all this is saying is that if we have two identical circles, we also kind of discussed this concept before, right? If we have two equal circles, okay, and then equal chords inside of equal circles, so let's just say this here. Oh, no, actually, sorry, they've chosen it for us already. They say that this is equal to this, okay, and if these two are equal, okay, the angle that they subtend is this guy, and this would be equal to this. Okay, so this is a very specific case. Equal circles, equal chords, subtending an angle, those angles would be equal. Okay, because equal chords in non-equal circles won't necessarily subtend equal angles. Okay, equal chords in two different circles, different sizes of circles, will not necessarily subtend equal angles. However, equal chords inside of equal circles would definitely subtend equal angles. Okay, let's look at theorem 5. So theorem 5 is opposite angle cyclic quad. Okay, so we're getting into a cyclic quad. Let us discuss what is a cyclic quadrilateral. Okay, so a cyclic quadrilateral comes from the word cyclic, meaning it is found within a circle, quadrilateral, meaning it is a polygon with 4 sides. So a cyclic quadrilateral is basically a quadrilateral that fits perfectly into a circle. Its 4 corners, the 4 corners of this quadrilateral, touch the circumference of the circle. So this is an example of a cyclic quadrilateral. Okay. This here is not an example of a cyclic quadrilateral. Ignore, just pretend that they don't go over. Even though 3 sides of this quadrilateral touch the circumference of the circle, the 4th side does not, and therefore it is not a cyclic quad. Okay, this is not a cyclic quadrilateral. However, this is definitely a cyclic quadrilateral because all 4 corners of the quadrilateral touch the circumference of the circle. Okay, so that's basically what a cyclic quad is. It's a quadrilateral which is surrounded by a circle. Okay, so let's look at the theorems that when it comes to cyclic quadrilaterals, okay, which we'll work with often. Opposite angles of a cyclic quad are supplementary. So remember, this keyword supplementary means what? This keyword supplementary means that they add up to 180 degrees. Okay, so if we have to look at this case, do they have any? So if we have to look at this specific case, all it's saying is that if angle Q, if angle Q, okay, is equal to X, then angle A, which is opposite to it, would be 180 degrees minus X. Okay, if angle D is Y, then angle U opposite to it would be 180 degrees minus Y. Okay, that's what this is saying, that the opposite angles of a cyclic quadrilateral are supplementary. So this is the first property of a cyclic quadrilateral, which we're learning. Let's move on. Okay, so this is the converse. So all converse theorems, okay, are basically the theorem but backwards. Okay, so whatever was implied in this case, okay, opposite angles of a cyclic quadrilateral are supplementary. So this here requires you to have a cyclic quadrilateral first. Okay, it requires you to have a cyclic quadrilateral first, and then you can use the theorem to say, since this is a cyclic quadrilateral, its opposite angles are supplementary. So therefore, I can follow the rule that if this is Y, this is 180 minus Y. Now, the converse is if you don't know it's a cyclic quadrilateral. So in this case, you just know that it's a quadrilateral. It says, if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. Yeah, so basically, if you can prove in this random quadrilateral, there's no circle around it right now, okay, so we don't know that it's a cyclic quad. So I can't just say I have this as alpha, and I don't have this. I don't know what the value of that is. Y, I don't know what the value of Y is. Because this is the quadrilateral, I can't just go and say that this is 180 degrees minus alpha, because it's not a cyclic quadrilateral. I don't know yet if it's a cyclic quadrilateral or not. So I cannot just assume that Y is 180 degrees minus alpha. Okay, this is just a regular quadrilateral. It's not a cyclic quadrilateral because it's not surrounded by a circle, nor have we proved it to be a cyclic quadrilateral just as yet. Okay, so that's exactly what we're going to do. We're going to try and prove that it's a cyclic quadrilateral. And one of the ways in which you can prove it's a cyclic quadrilateral is if you can prove that that angle is 180. So separately, not using this reason, not using the opposite angles of cyclic quadrilateral reason, some other way, maybe this diagram is not complete, maybe there's other things here that help you determine it, whatever, all right? But you somehow prove that the value of this angle is 180 degrees minus alpha without using opposite angles of cyclic quad for this specific quadrilateral, okay? Now that we've proved that that's 180, now I can see that these opposite angles of this quadrilateral are actually supplementary. How do I know that? Because this is alpha, this is 180 minus alpha, that means that when you add those two, they add up to 180. So now I've proved that the opposite angles of a cyclic quad are supplementary. Sorry, I've proved that the opposite angles of a quadrilateral are supplementary. And since the opposite angles of this quadrilateral are supplementary, that means it's a cyclic quad. Because a cyclic quadrilateral, okay, its opposite angles are supplementary. Okay. So keep that in mind. This is the converse. This is actually very important. This converse, maybe the previous were like, you know them, you don't know them. They're mostly not going to test them, but these get tested all the time, proving that something is a cyclic quadrilateral. So you have to understand this. Okay, please keep in mind Q is alpha, Y is 180 degrees minus alpha. They were proved separately. They weren't related to each other whatsoever. Somehow Q was proved to be alpha and Y was proved to be 180 minus alpha, not using the opposite angles of cyclic quadrilateral, because again, we don't know that this is a cyclic quadrilateral just as yet. But now that we have those angles, we're like, oh, okay, the opposite angles are supplementary. Thereafter, we can conclude, okay, this is definitely a cyclic quadrilateral because we've proved that the opposite angles are supplementary. Okay, that opposes to this, where here you are told it's a cyclic quadrilateral, and then you can use the properties of a cyclic quadrilateral. So if you had the value of that as y, right, then you could easily say that u is 180 degrees minus y because you are given the fact that it's a cyclic quad. Okay, so I hope that that distinguishing between the two is making sense to you. Okay, let's move on to the second theorem of a cyclic quadrilateral, and that is the exterior angle of a cyclic quadrilateral. So again, this first one is assuming that you do know and it is given that it's a cyclic quadrilateral. Okay, so the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, so let's have a look at this diagram. Okay, and we can see, so remember we discussed exterior angle, so we discussed it of a triangle, right? Not just any angle like this here, for example, is not an exterior angle. It may look like it's on the outside of the triangle, but we won't refer to that as an exterior angle. It needs to be continuing the straight line of the shape, and then that angle would be the exterior angle. Okay, so that's why in this case, as you can see, the straight line here is continued, and therefore we have this exterior angle, and they called it X. Okay, and it's equal to what? It's equal to the opposite interior angle, so that would be opposite inside angle, which is alpha, and that's X. Okay, so these are equal. They're not supplementary, they are equal. Okay, so the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, hope that makes sense. Let's look at the converse. Now, just say we don't know that it was a cyclic quadrilateral. However, we can prove that the exterior angle of some quadrilateral is equal to its opposite interior. Then we can conclude that, okay, yes, this is a cyclic quad. So they say here, if the exterior angle of a quadrilateral is equal to the interior opposite angle, then the quadrilateral is cyclic. Okay, they didn't discuss the third one. Let us just quickly discuss it. Okay, let's have a look at we've discussed it already. Did they form it? They didn't form it part of a cyclic quadrilateral. Okay, let's use the Lies theorem 4, okay, to show another property of a cyclic quadrilateral. Okay, in a cyclic quadrilateral, let's draw one. Okay, this is a cyclic quadrilateral. If we have to draw in our diagonals, they would look like this. Okay, so that diagonal and this diagonal drawn in. Now, in this cyclic quad, let's try and we can change this to it. Okay, if we look at the cyclic quadrilateral, the diagonals are drawn in. Okay, so let's pay attention. Let's label it. So let's call it A, B, C, D. Let's have a look at this chord. Okay, it's a chord, right? It's a line drawn from one end of a circumference to another end of a circumference. It's a chord. This chord, and let's have a look at the angles that this chord subtends. Okay, so it's a bit tricky. There's many lines, but you can use your fingers, right, and follow the point. So, for example, chord AD. Okay, you put your finger on A, put your finger on D, and you follow it to one angle. So I can follow it to angle B. It's there and there. Okay, so we can all agree that chord AD subtends angle B. Okay, not the whole thing, but this part of it. Okay, in fact, we'll just call it X. Let's call it X. Okay, I think we can all agree that. So now it doesn't just subtend that angle. Chord AD actually subtends another angle, and that is angle C. So we follow it from A to C and from D to C, and it creates another angle. Okay, and if you remember correctly, let's just do this. Why is that as also X? Because it's subtended by the same chord. So if you remember correctly, we discussed that angles subtended by the same chord are equal. So in this case, these angles are equal. Okay, and we call them angles in the same segment. According to theorem 4, we said that these are angles in the same segment. Why? Because they are subtended by the same chord. So this should now be clear to you that in a cyclic quadrilateral, okay, angles in the same segment are equal. In a cyclic quadrilateral, angles in the same segment are equal. So if we can prove that any two angles, or the two angles created by the diagonal technically, but subtended by a chord are equal to one another, then that quadrilateral is a cyclic quadrilateral. Okay, so here, these angles are subtended by the same chord. Okay, it doesn't just end there with a cyclic quadrilateral. Let us work with a different chord. Let us work with CD as our chord. CD as our chord. And I'm going to consider the angles that CD subtends. I'm going to follow it to A, from C and from D, and you'll be able to see that it subtends which angle? This guy here. Call it Y. But CD doesn't just subtend one angle, it subtends two. At angle B, CD subtends an angle as well. And we can call this Y as well, because again, it is subtended by the same chord. So they are equal to one another. We can even use a different chord. Let's use the top line as a chord. Let's use BC as a chord. If we use BC as a chord, let's consider the angles it subtends. It subtends angle D. Okay, it subtends it. So angle D here, we can call it, we can call this Q. Okay, and chord BD doesn't just subtend one angle, it subtends two angles. Okay, it subtends angle A as well, and they would be equal. So this is also Q. Okay, then finally we can use the last one we haven't used as a chord. Side AB, if we use that as a chord, okay, it subtends two angle BD, and using line BD and line AD. Okay, it subtends this angle, which is we can call it P, I guess. Okay, and it doesn't just subtend a single angle, it subtends another angle here, which we can call P as well. Okay, so oops. Okay, so that's how we utilize the diagonals of a cyclic quad. I hope that makes sense. All right, so discuss many concepts that we need to know. Firstly, what a cyclic quadrilateral is. Secondly, what the diagonals of a cyclic quadrilateral look like. Thirdly, we need to know that angles subtended by the same chord or angles subtended by equal chords are equal. Okay, and that's the theorem that we used here 4 times, okay, to create equal angles. So keep it in mind that when you have a cyclic quadrilateral, you can use angles in the same segment 4 times, because you can use the different chords, the different sides, or the different chords of the quadrilateral, of the cyclic quadrilateral. Okay, and these are the angles which are equal to one another, okay, within the cyclic quadrilateral. Okay, so here, excuse me, we utilize the concept of angles in the same segment. And we said that in a cyclic quadrilateral, what's the reasoning? Yeah, but your reasoning here also is going to be angles in same segment. Okay, and the converse of that, right? The converse of that is when you have a regular quadrilateral, Okay, and if you have both diagonals drawn in, right, this doesn't work with one diagonal. You have to have both diagonals drawn in. So if you can prove that this, okay, is equal to this, okay, then you can say that actually it is a cyclic quadrilateral. This is not going to be a circle, but it's fine. Okay, then you can actually say that it's a cyclic quadrilateral because why? Angles in same segment. So if you find a quadrilateral, okay, so if you have just a regular quadrilateral and you can prove that its angles in the same segment are equal, then you've proven that this quadrilateral is actually a cyclic quadrilateral. Okay, interestingly enough. Okay, so yes, that's the fourth property of the cyclic quadrilateral. Let's move on to theorem 7, tangent perpendicular to radius. Okay, so it says a tangent to a circle is perpendicular to the radius at its point of contact. So what is a tangent line? A tangent line is a straight line drawn on the edge of a circle in this case, okay, that only touches this the circle at a single point. Okay, so examples of tangents could be a line passing. It's not going to let me, but I just do that and pretend it touches once, like somewhere there. Okay, perhaps like somewhere here. Yeah, this is not great, but I can just move it like there, and it only touches once, or like there. So there's many examples of tangent lines, right? Okay, so that's what a tangent line is. So let's have a look at this tangent line drawn here. Okay, so here's the tangent line, and it basically says that tangent is always perpendicular to radius. So it's not just perpendicular to any radius, like if I had to draw this radius, okay, I can't say that these two are perpendicular to one another. That doesn't make any sense. Okay, it's perpendicular to the radius that is drawn from the point of contact with the circle. So basically, where the tangent line touches the circle, if you have to draw a radius from that point, obviously a radius is from the circumference to the circle, sorry, from the circumference to the center. If you draw a radius, just know that that tangent is perpendicular to that radius. Radius perpendicular to tangent. Let's look at the converse. A line drawn perpendicularly to the radius at the point where the radius meets the circumference is a tangent to the circle. Okay, so furthermore, here it is given that this is a tangent. However, in this case, it's not given that it's a tangent. However, it's given that it's 90 degrees. So since this is a radius and it's perpendicular to a line touching at the point where the radius touches the circumference, then you should know that that line is definitely a tangent line because it is perpendicular to the radius drawn from that point. Okay, so that's the converse. Let's look at theorem 8. Tangent from same point. It says two tangents drawn to the circle from the same point outside of the circle are equal in length. So the example looks like this, okay, where you draw two tangents and they actually meet each other. Okay, so that's why you say they originate from the same point. Okay, so here this bottom tangent is a tangent at P, and this tangent to the right is a tangent at R. Okay, and they both originate from K, meaning they're actually going to make contact at K. Okay, and what's the property of this type of these tangents? Okay, it says that they are equal in length. Okay, so basically what you should know is that this side is equal to that side. Okay, the length. So those are the reason for that is tangent from a common point. Okay, let's look at theorem 9, tan-chord theorem. Okay, tangent chord theorem. So angle between tangent and chord drawn from point of contact of tangent is equal to the angle subtended by the same chord. So let us do our own thing for a second. Okay, so let's draw up our own little circle and let's discuss this tan-chord theorem thing. Okay, so firstly, I'm going to draw in my tangent. Okay, so let's just say it's at A, where this line makes contact, this tangent line makes contact with the circle at A. So tan chord theorem involves a tangent and a chord. Okay, so the next step is we have our chord. So tangent and chord. So from the point of contact of the tangent with the circle, which is at point A, where the tangent touches the circle, we're going to draw a chord. Let's draw a chord this way. Okay, so this is a chord. Okay, it's a chord drawn from the point of contact of the tangent with the circle. And what tan chord theorem says is that the angle between the tangent and a chord drawn from that point of contact of the tangent with the circle, this angle here between the tangent and the chord, angle between tangent and chord, which again is this angle, let's call it theta. Okay, it is equal to the angle subtended by that chord. The angle subtended by this chord would be any angle that's subtended from here. So let me subtend an angle here. It would be something like this. So in fact, this angle here is theta. Okay, let's go that again through one more time. Through that one more time. Tan chord theorem involves a tangent. I drew my tangent at A. Okay, tangent line only touches once. It touches at A. And tan chord theorem states that the angle between the tangent and the chord is equal to the angle subtended by the chord. So here I drew it. I drew in my tangent first, then I drew in my chord, and then I created, okay, this angle between the tangent and this chord. Okay, it's equal to the angle subtended by that same chord. Okay, not any chord, the same chord. So the angle between tangent and chord is equal to the angle subtended by that same chord, and this angle subtended by the same chord is here. Right, let's call it B. Okay, so I hope that makes sense. Please, if you have any questions, please do ask. Okay, I'm going to do the same example, but I don't want to ruin that first one. Okay, so let's just say that was theta. But now one could also say that I could create this angle as an angle between tangent and chord, okay? But in this case, right, my chord, let's not do that. In this case, I'm using a different chord, right? What chord am I using? Now I'm using this chord. BA, AB. So if I use AB as the chord, yes, most definitely. The dark blue lines are also chords. Definitely. The dark blue lines are also chords. Okay. However, okay, yeah. Okay, 100%. You're correct. That's what we're doing in this next example. Okay. So now we're dealing with AB as a chord. 100%. Okay. So when we deal with AB as a chord, let's call this alpha. Now we have to consider which angle does AB subtend, because now I'm considering the angle between tangent line and chord, and I've changed my chord. I'm using chord AB as well. Instead of using chord AC, I'm using chord AB. You could use both, right, depending on the question. Okay, and now I have to consider, okay, I have angle between tangent and chord. Now I have to consider which is the angle subtended by that chord. Again, you can use your fingers, right? You can use your logic, whatever you want to use, but B and A, AB, which angle does it subtend? Right, if we follow these lines, it subtends angle C. Okay, and angle C is here. We can call this guy alpha. Okay, so angle between tangent and chord is equal to angle subtended by the same chord. That's explained here in this diagram, and I hope that makes sense. So let's go back to this. Okay, angle between tangent and chord drawn from point of contact of tangent is equal to the angle subtended by the same chord. Okay, they have a tangent here. Converse theorem 9 between. Okay, before we discuss the converse, let's have a look at this. So here we have angle between tangent and chord. Alpha is going to be equal to angle subtended by that chord. This is a normal example. Definitely nothing wrong with this example. Okay, absolutely not. This is incorrect. Okay, the reason for that, and you have to be careful for this, you have to look out for it, is that let's call this A, let's call this B, let's call this C. C is not a chord. Sorry, AC is not a chord. C is not on the circumference. Okay, so look out for this. It might look like tan chord theorem, Okay, but it can be very confusing, especially when there's 6 million lines in front of you. Okay, so AC is not a chord. Okay, so this angle here is not an angle between tangent and chord. It's just an angle between tangent and whatever this line is. Okay, so please look out for this. This would not obey tan chord theorem because, again, AC is not a chord. Excuse me. Okay, so let's look at the converse theorem 9. Angle between line and chord. If a line is drawn through the end point of a chord, making the chord an angle equal to an angle in the alternate segment, then the line is in a tangent to the circle. Okay, so this one is also really important because it's asked a lot. Okay, so you'll be dealing with a triangle. Okay, and a fourth line. Excuse me, and a fourth line drawn through one of the points. A fourth line drawn to one of the corners of your triangle. Now, if you can prove that any of these angles between the line and this side of the triangle, or the line and this side of the triangle, is equal to the angle subtended by that same line. Okay, so I'm not using chord, okay, because we like not in a circle for now, right? Remember, it's like this is not given. Okay, they're not going to draw in a dotted circle for you because then it's obvious. Okay, it's given like this. Okay, and it will be in a mix of many other different lines, okay, depending on what you're doing with, maybe a circle within a circle and a bigger circle, whatever it is, right? But you'll somehow end up with this, and they'll want you to prove that that, okay, I forget the exact question, but I'm pretty sure it's something like that when a circle passes through, basically they want you to prove that a circle can pass through BCA. Okay, however they word it, I forget, but they want you to prove that a circle can pass through BCA. Okay, as you can see, I drew a perfect circle and it actually does pass through it. Okay, but they'll want you to prove that a circle passes through BCA. Okay, and the way to do this is, wait, let me just think for a second. Okay, when we do the question, we'll get there, but it's basically the converse of tan chord theorem. And in this case, you will actually be using the reason converse tan chord theorem. So you will be required to prove that this angle theta, okay, is equal to this angle. Okay, the opposite angle, it's basically subtended by line AC. Okay, so the line between your supposed tangent, oh, sorry, yeah, you'd have to prove that it's a tangent through, it's a tangent at a of a circle passing through BCA. That's how the question will be phrased. They'll want you to prove that TAN, the line TAN, is a tangent, okay, at a circle which passes through BAC. Okay, so that's what we are proving that it's a tangent. Okay, so here we assume, or it's given, right? It's given in the question that that's a tangent. TAN is a tangent, and then we can use tan chord theorem, right? We can say that the angle between the tangent and the chord is equal to the angle subtended by the chord. However, here it's not given that's a tangent, and the question will be phrased that they want you to prove that TAN is a tangent to a circle that passes through ABC. Okay, and they don't have to draw in that circle as well. They won't, right? They were not going to give you that circle. So again, if you can prove that the angle between our supposed tangent, or the line TAN, and the line AC, or chord AC, right, is equal to the angle subtended by line AC. Okay, if you can prove that these two are equal, okay, without using the tan chord theorem reason, of course, like you can't say that this is equal to this because of tan chord theorem, because we haven't proved that this is a tangent as yet. Okay, so if you can prove them separately using different reasons, prove that they're equal, then you can say therefore TAN is a tangent, okay, to the circle passing through ABC. Why? Reason for that: converse tan chord theorem. Okay, converse tan chord theorem. Okay, cool. Okay, so we discussed all our properties. If you, while you're doing questions, right, during the rest of this term, if you're confused with any of the theorems, come back to this video and watch this explanation of these theorems once more. Okay, because you have to, like, of course, if you've practiced a few examples by now, you know that it's impossible to answer any questions. If your theorem understanding is not good, if not perfect, right, then you're not going to be able to implement that into the diagram. Right? Normally, most students understand all the theorems like very well, just implementing that into the diagram, which can get tricky. Okay, let's look at this question. 1 second. Okay. Let's look at this question and let's try and solve for it. Okay. It says that GFE is a double chord and H1 is equal to 75 degrees. Let's fill that in. Okay. H1 is equal to 75 degrees. GFE is a double chord. Okay. GFE is a double chord. Okay. I think all they're trying to tell us there is that GFE is one line. Okay. So it's a straight line and it forms a chord in the first circle and it forms a chord in the second circle. Okay. So that's what they mean. Determine the value of D. Okay. They want us to calculate that value. Okay. So there's many ways we could do it. So firstly, right, remember we have two circles, okay? And then within those circles, we have actually quadrilaterals, okay? So for example, this here could be seen as a cyclic quadrilateral, okay? HCGF, right, is a cyclic quadrilateral. CDFE or CDEF, okay, this is also a cyclic quadrilateral, okay, within the second circle. Okay, so we can use properties of cyclic quadrilaterals. There's also like properties of straight lines. Again, various ways we could probably solve it. The quickest way is to use properties of cyclic quadrilaterals. So let's look at HC. Let's look at this first circle on the left. Okay, you can see that H1 is actually, because this is the straight line continuation. So H1 is actually an exterior angle of the cyclic quadrilateral. So I can use the ruling of opposite interior angles of cyclic quadrilateral is equal to the opposite exterior angle. So I know that this is also 75 degrees. Okay, now let us put that into words. Let us show how we're going to answer that. So I've said F1 is equal to H1, right, which is equal to 75 degrees. And I have to state a reason. Okay, so in this case, I will just say opposite angle of opposite angle of cyclic quadrilateral. So there's no need to write everything in full. Cyc quad is perfectly fine. Instead of using the word angle, you can say angles. Instead of saying full opposite, you can say OPP. Okay. I'm not sure if it's in the, I'm pretty sure it's in the examination guidelines, right? There's a table with all the valid rules, right? All the rules that the way they want you to phrase it and the way they want it. Okay, in the paper, so you can have a look through those. And you'll find that this is what they would have for opposite angle of a cyclic quad. Okay, so we know that that's that. Now, this cyclic quad, okay, because this is a double chord indicating to us straight line, okay, it is also an exterior angle to the second cyclic quadrilateral. Okay, because it's a straight line continuation. So this here is an exterior angle to the cyclic quadrilateral. So once again, we can see that this exterior angle of the cyclic quad is equal to the opposite interior angle at D. So I'm going to say angle D is equal to angle F1, okay, which is equal to 75. And the reason is the same, opposite angles of cyclic quadrilateral. And therefore, we've proved D. Okay, so D has a value of 75 degrees. Okay, that's the quickest way to solve it. Okay, yeah, like alternatively, you could like use the fact that this is a straight line, okay, and then say 180 minus 75. That would give this 15 plus 90, 105, I think. Yeah, 105. Okay, and then use opposite interior angles of cyclic quad to get that to 75. Do the same thing here. Get this as 105. Okay. And again, use opposite angles of cyclic quad as supplementary to get that as 75. Okay. But obviously you can see that that's a much longer way. If we just use exterior angle of cyclic quad, that it solves much quicker. Okay. Let's have a look at this one. Just to answer these questions, right? These are just some simple questions just to like sort of get a taste of these questions and practice our theorems a little bit before we move on to a hectic question. Okay. Given circle GHJK with GM perpendicular to HJ and GL perpendicular to LJ. So I don't think any of that information is given in the diagram. So let's translate it over. So the first thing is it's a circle. That's fine. GM perpendicular to HJ. This is perpendicular. And GL perpendicular to LJ. So these are perpendicular. G3 is equal to 24. G3 is here. This guy is 24. Okay. Is quadrilateral GLJM a cyclic quadrilateral? So let's highlight which cyclic quadrilateral they're talking about. GLJM. GLJM. This guy here. Okay. They want to know, is this a cyclic quadrilateral? Okay, so remember with cyclic quadrilateral, you have 4 options. Okay, we'll go through it here as well. Wait, did I say 4? You have 3. Sorry, you have 3. Proving a cyclic quadrilateral. Okay, so again, we'll go through it in this more complicated example. I think this is a complicated example here. Right, we'll go through it here as well. But let's just look at the rulings for now. Okay, so proving that something's a cyclic quadrilateral, you have 3 options. You can either prove that the opposite exterior angle of a cyclic quad. Okay, so you have 3 options, sorry, which are basically the 3 properties of a cyclic quad. So number 1, opposite exterior of a cyclic quad. Number 2, opposite interior angles of a cyclic quad. Number 3, angles in the same segments. Okay, so remember, you are required to prove these. You cannot assume them. Prove, or prove this one, or you can prove this one, right? You just don't have to prove both 2 or 3. You can just prove one of them. Okay, so opposite exterior angle of a cyclic quad, this you would then say is equal to, you would have to prove that it's equal to the opposite interior angle. Okay, so if you can prove that the opposite exterior angle of a cyclic quad is equal to the opposite interior, the opposite exterior angle of a quadrilateral is equal to the opposite interior angle of a quadrilateral, then that quadrilateral is a cyclic quad. Okay, so we have these 3 options. Okay, and in the second one, opposite angles of a cyclic quad, if we can prove that 2 angles opposite each other in a quadrilateral are supplementary, meaning they add up to 180, then it is a cyclic quadrilateral. Then number 3, angles in the same segment. If we can prove that 2 angles which are in the same segment, if we can prove that they are equal, then we can say that this is a cyclic quadrilateral. Okay, just keep in mind for the last one, this is a hint, right? It helps you because it says both diagonals have to be given. So basically, if both diagonals are not given, you cannot use 3, and then you only have 2 options. It makes your life easier. Okay, so let's have a look at this, right? So we have, what happened to our... Okay, we have quadrilateral GLJM, and they want us to prove if it's a cyclic quadrilateral. So the first thing you can actually do is assess whether you have both diagonals or not. So here we don't even have a single diagonal. Diagonals would look like this. They're drawn across the shape. Here we don't even have a single diagonal, so we cannot use number 3. So number 3 is out. Let's look at the first 2. So firstly, we can prove that opposite interior angles are supplementary, or we can prove that exterior angle of cyclic quadrilateral is equal to the opposite interior angle of the, sorry, not cyclic quadrilateral, quadrilateral. And then if that's true, then it would become a cyclic quadrilateral. So we can use either one. Okay, so we can, because this is, so let's look at the only angle we have in our cyclic quadrilateral, which is this one, 90, right? Angle L. So if we can prove that somehow this is 90, because why it needs to be 90? Because of 90 plus 90, this needs to be 90 plus 90, it needs to be supplementary. So if it's supplementary, then yes, of course, we've proven it, and it would be a cyclic quadrilateral. So if we can prove that M2 is 90, then 90 plus 90 would add up to 180, and it would be supplementary, and it would be a cyclic quadrilateral. So that's the first way. And yes, we can prove that M2 is 90 because it's a straight line. So I can say that M2 is equal to 180 degrees minus M1. What's the reason for that? Angles on straight line. Okay, therefore, M2 is equal to 90 degrees because 180 minus 90. Okay, then we can say that L plus M2 is equal to 90 plus 90, which is equal to 180. Therefore, GLJM is a cyclic, or we can just say cyc quad, and we give a reason. Our reason for this is opposite interior angles are, so now this, in this case we have to say they are supplementary. We don't just say opposite interior angles of cyclic quad. Supplementary, because we're proving that it's a cyclic quad. So we say, what's our reason? Opposite interior angles are supplementary. Okay, another easier way you could have done it is, this is an interior angle. This here, M1 is an opposite exterior angle. Okay, since it's an opposite exterior angle, you could also say that. This is 90, given. All right, this is 90, given. L is equal to M1, therefore it's a cyclic quad. Why? Opposite exterior angle of cyclic opposite exterior angle is equal to opposite interior angle. Done. Then they ask, is quadrilateral GLJH a cyclic quad? Is the quadrilateral GLJH? Let's consider GLJH. Okay, this whole thing. GLJH, is this a cyclic quadrilateral? So one way we could use to solve this is, obviously we know L. Okay, so if we can get the value of H, right, if we can prove that this is 90, then we can prove that it's a cyclic quadrilateral. If we can somehow prove that H is 90, then we can prove it's a cyclic quadrilateral. So let's try and get the value of H. Okay, I'm going to say in triangle, this is how we can get it. In triangle GHM, okay, angle H is equal to 180, and I'll give the reason for this now, minus G minus M1. The reason for this is angles in triangle, sum of angles in triangle. This is the reason. Sum of angles in triangle. Okay, so therefore H is equal to 180 minus 24 minus 90. So it's 90 minus 24, 70, 66. So it's 66. Okay, so since H is 66, okay, that's going to tell us, hey, this is not a cyclic quadrilateral, because now I'm going to say in quadrilateral GLJH, okay, angle L plus angle H is equal to 90 plus 66, okay, which is equal to 156, and then I can say which is not equal to 180 degrees. Therefore, GLJH is not a cyclic quadrilateral. Okay, why? Opposite interior angles are not supplementary. Okay, that's that. Okay, cool. So let's end it there. I hope that that sort of tickled your guys' taste buds for some Euclidean geometry questions, some easier questions, right? We will finish all of these, but just to practice them. And then, yes, we can do something that looks like a complete abomination and try our best to just improve our approach to these questions. Okay, ultimately, I would say that the best thing to improve yourself in this section is practice. Okay, now that we have covered all the basics, right? Because remember, I told you in the start, like one of the most important things, or maybe like the most undermined thing, is to make sure that we understand the basics. So understand the basics, and I'm talking about every basic, right? From grade 11, I'm talking about parallel lines. I'm talking about understanding what is a transversal. Okay, of course, bisect theorem and all of that. Okay, that's like the easy part. Okay, and then so make sure you understand all the basics, and then you just go into practicing questions, right? And that's where I come in. Hopefully, I can improve your approach to questions, right? Let's see if we can look at questions differently, or make sure that we get certain things that we maybe keep on missing out on, or whatever it is. But yeah, for now, let us end it there. Thank you guys so much for joining. Yeah, I'll see you guys next week, where we'll continue with Euclidean geometry. Okay, cool. Thank you guys so much for joining. Jazakallah khair. Assalamu alaikum and goodbye.